So space technology, everyone. Space technology is actually a significant part of our daily lives, whether we are aware of that or not, from our GPS in our cars, it walks in front of me, to our smartphones. AxelSpace is a Tokyo-based startup that aims to create a wave of innovation in space technology by creating microsatellites for businesses. And we're going to hear more about that by the space systems engineer, Lucas Brémond, who's going to tell us a little bit more about this really creative and funky startup in Japan. Lucas, the floor is yours. Warm round of applause.
Hello, everyone. I'm very happy to be on this stage today. I'd like to thank you, the ArabNet, for inviting me. So my name is Lucas. I'm French, currently living in Japan. And I'm working for a startup company which is developing, as Sarah said, microsatellite. And I really felt the previous topic about the makerspace was really interesting and really inspiring because, first, space is in the name, so that's interesting first, but also, actually, it's closer to that than what you think. So before starting introducing what we're doing, I think to better understand how the space tech is today is to understand how it evolved from the inception. So I'll very briefly introduce how it evolved from, let's say, the 50s to nowadays. So if you're already a space geek, I'm sorry, it might be a bit simplistic, but so that everyone is on the same page. So what you see here is actually the first American EVA, which means the extravehicular operation. And it was performed in '64 by the Americans. Between this time and the next step, where the American landed on the moon, only 5 years. Actually, it was 65, and then 69 was Apollo 11. This picture is not Apollo 11. It's actually another one, which I like more, because the guy played golf on the moon. And if you really think about it, do we still play golf on the moon? Nah, not much. Actually, nothing is really happening in that dimension nowadays, because this technology was developed because of the Cold War. It was a race between Russia and America, and basically, when it's in terms of national pride, money doesn't count much. So they invested tons of money to make this thing achievable. One of the pictures I really like is that they also sent jeeps on the moon. And actually, not so many people know about it, but it's awesome. I mean, can you imagine like some guy driving this thing on the moon? That actually happened many times. Does it happen today? No, because again, we don't have this political incentive anymore. And then after, starting from the 70s to the 2000s, you had the Space Shuttle. It was an amazing program, but the problem is that it was so expensive that it basically ate all the other resources for other space programs. So it was a beautiful piece of machinery, but it kind of, restrained NASA from doing other things because of its extremely high cost. And so, since then, man has never been farther than low Earth orbit. And low Earth orbit means the ISS, the International Space Station. Another thing, why everything is going a bit slow on space, is actually you have to think that space is harsh. Full of radiation, the thermal environment is really hardcore. Just to give you an example, if you have a structure in space, one part of the structure is in the shade of, let's say, Earth, and the other one is seeing the sun. The sunny part will be like plus 150 degrees. The shady part will be minus 150 degrees. So you have 300 degrees of thermal gradient, which means thermal difference between the two edges. And this is inducing a lot of constraints. This is not something we have on Earth. So this is Curiosity. This was a rover sent by NASA, by JPL, on Mars. And it's a beautiful piece of technology, really. But if you really think about it, the computer on board is actually the same generation of this iMac G3. It's kind of late. So you see, the thing is to build such reliable systems, you have to go slow, you have to make reliable technologies. And that's why we're a bit behind in this industry when you compare with your smartphones, for instance. Actually, if you think about it, your smartphone is much more powerful than all of the satellites that are already up there. So what is changing now is we have consumer market. Everyone has a smartphone, I guess, and this actually makes lots of things cheaper for all the industries. Before, NASA invented technologies for the Apollo program, and you had this top-down approach when all the technologies invented for Apollo, for instance, were then open to a broader market. For instance, let's say, or not only actually Apollo, but like the GPS, for instance. This was military first, and then you use it, everyone is using it for navigation. But nowadays, we have the opposite effect. Because of the global market and because of this technology that is arising, actually now this technology is pushing the space market again. And this is very interesting because now is the perfect timing to kind of start again a new space quest, if I may say. For instance, think about this. I mean, the Pi that got released, the Pi 3 got released, got announced a few weeks ago, and the Arduino, they cost $20, and they are more powerful than a lot of space systems. This is amazing. Of course, you cannot send those directly to space. They will die pretty quickly from radiation. But that's a good base, actually. And some people are also using those things and modify them a little bit to make them more reliable and use them in satellites. And it's very interesting because you can have access to all this computing power for a very low fraction of the cost. So what's important today? I guess that's everything about this conference is the Internet of Things, the data, the big data. So data, yes, data is getting a more increasing part in our business. And I think if you want to aggregate data, the best viewpoint is from space, because you have access to lots of area with one machine. So you can aggregate a lot of things quickly, and since you're orbiting, actually you don't have to push like drones again. You don't have to repropel. You don't have to like charge or whatever. Everything is kind of automatic because of solar panels, because orbiting means basically the drag is kind of low, so you don't get down that easily. So you have kind of a permanent system up there that can help you getting fresh data. The other thing that's changing nowadays is actually you have new launch services, launch providers arising, private launch providers. So I guess everyone knows SpaceX, which is the big guy right now, but actually you have other companies that are trying to develop rockets. And for us satellite makers, it's a good news because it's going to drop the price down, and it's going to give us access for a cheaper cost to orbit. And this is happening today. Actually, even some part of those rockets are 3D printed. So one big thing in space technology nowadays is called the off-the-shelf. It means that we stop reinventing the wheel all the time. We stop designing from scratch all the components, but you buy or you take already developed components and you plug them. And that's very interesting because by using this approach, you can generate a lot of different platforms using the same components, so you reduce the cost. And this is what we are doing. So today I'm going to talk about the company I'm working for, AxelSpace, which is based in Tokyo. And I hope this talk will kind of help you realize that actually this industry is now accessible to lots of entrepreneurs that do not necessarily have all the inertia that NASA has. We are actually a very small team. I will explain later. And, well, first, we're based in Japan, in Tokyo, which is interesting because think about it. All these big NASA centers, they are always, in rural areas. They need a lot of space. Actually, our office is in one of these towers. We develop our satellites in the office. We don't need much space because they are small. So we don't need all these increasingly important resources that most makers need. And one thing, actually, the concept of the key concept of the company can be pictured with this graph. If you plot reliability versus cost, what happens actually in space science is at some point you will have this very, very flat curve at the end, which means that you can add a lot of money, but you will not get so much in terms of reliability. The problem is that when you want to send humans to space, for instance, you have to be sure 99.99% that your rocket is not going to fail. So in our case, we are actually developing microsatellites. We are not really trying to reach this crazy reliability. So the whole point is actually the reasonably reliable concept. We are a bit in the middle. We try to be reliable enough so that we don't lose our system right away, but we try to keep the costs reasonable so that we can produce a lot of systems. And if one fails, we can recover, because we can sell many others for the same price. So the video is not working, but it's fine. So this is the kind of systems we are building. Those are microsats. They are around, we have different shapes and size, but let's say they are about 50 centimeters. So when you compare to a big satellite, it's pretty small. And that's the team. So that's all of us. And this is our little baby, which is now in space and taking pictures. I'll show you some of them later. So the team is mostly Japanese, but we are getting internationalized. I'm French. There is an Italian guy, Indian guy there. So, and actually, we are trying to welcome many people from the world. So if you're interested, give me a shout. What we're doing is actually we are developing from everything, from soldering to operations. So because we can control everything, we don't really need to pay all these super expensive space infrastructures. We can keep the price low. And we are reusing a lot of off-the-shelf components. Let's say chips, for instance. Instead of developing our own CPU, we are reusing CPUs that are sold for various applications, not only space, but for automotive or cars or whatever. We are reusing them. So we can have access to all this technology right away. So if you compare the size, that's a big guy. That's typical. And it costs about $300 million. Our little thing here costs 3, and it's cute, and it's small. And actually, it can do many things. Another way for us to keep the price down is actually testing. For instance, when you have like this NASA-style testing, they really go into these big chambers. They pay a lot of money to manage them. In our case, we don't really have access to that. So we just go out. That's to test the camera, actually a star tracker. It's looking at the stars. And we are at Mount Fuji. Actually, you can see the snow there, because the sky is very clear. So that's how we test the equipment. And here you have my friend Marco. He's testing the main camera of the next satellite. Actually, you can see he's in a park in Tokyo. Just testing. You don't need, those expensive things. Another concept we really use is called piggybacking. The thing is, we cannot afford a rocket completely. It's too expensive for us. One launch in a big guy right now can cost lots of millions of dollars, but we cannot afford that. So the idea is to hitchhike on a big launcher. For instance, here you see 4 satellites. The one we developed is the upright one. And then on top of those 4 little babies, you have the big, massive, classical one. And we just pay a few % of the launch cost, and we have access to the same orbit. So here it's, I hope it's going to work. Nope. Uh-oh. OK, so I'll restart quickly. So that was supposed to be a launch video, actually. So since I don't know why the video doesn't work, I'll explain what's happening. We are using old USSR missiles, actually. During the Cold War, USSR developed tons of missiles to mainly target the USA, but they didn't use them. So after the collapse of the USSR, they had this big stock of useless missiles. And they needed a way to refurbish them, because maintaining them in their silos was very expensive. So there's this venture, Ukrainian-Russian, that basically removes all the warhead things in this missile, and we just go in, and we have access to space with the same system. And the cool thing in this video is that actually it's not launched from a launch pad usually, but it's launched from a military silo. So it's pretty cool, but unfortunately, I don't know what's happening here. Another thing is that maybe you know NASA control rooms. You have lots of people dealing with a lot of systems, etc. In our case, it's not that we are trying to shift everything, but our system is much simpler. So actually, we don't need more people to operate our satellites. So what's really happening is that you have one guy, actually doing the operation, and the other two are just checking. And that's just actually after launch, because a few weeks after, we have a sort of kind of artificial intelligence that's taking over so that the real operator can do something else. So now our satellites are completely autonomous. We don't control them anymore. We just tell them where to look. That's, for example, a control system. I'm using my phone or my iPad or whatever, and I can just click wherever I want on the map, and I can take a picture. And this is because, the web is making things so much easier. All these platforms, all these tools are readily available. Why are we reinventing the wheel? We are just reusing a web interface and connecting with our custom-made system, and it works. So it's just some kind of Google map if you want, and we just click on where we want to take the picture. And in the end, actually, it's computing a lot of orbital trajectory things and taking the picture. But we don't need all these operation things. So a few examples of some of the satellites we developed. That was the first one in 2013. This is a very little baby. It's only 10 kilograms and 27 centimeters. This one got launched properly, and it's flying. We're still getting data, but unfortunately, the main camera got a radiation problem, and so we are not really using it anymore. But that was more a test, because we were preparing for the next one, which is Hodoyoshi one, is the one that we are actually using every day now. It's a bit bigger, 60 kilo, but its ground resolution is much better, and we can take very large 27 kilometers pictures with it. So let me show you some pictures we're taking with these little things. This is Saudi Arabia. We took it a few weeks ago. And what you can see here are all these agricultural crops. And what is interesting is that you can analyze those things, and you can start understanding what's happening if you can optimize, if you can improve, if you have damages or whatever. Another one is Suez Canal, for instance. I really like this one because you can even see the ships. And you can even see that their interval between the ships is kind of constant. It's very interesting. I love this one for the colors. Or this one is in Sahara Desert. It's beautiful. It's one of my favorites. It's called Richat structure. It's a very old geological thing. Yeah, that's my screensaver. Yeah, I'm from Paris, so I wanted to take a picture of my mom's place. So I just asked the satellite to point at it, and we took this picture. Or I love this one because actually those are real colors in Madagascar. This is a delta, which has this red thing. It's really cool. New Zealand, beautiful colors. Argentina, you have some glacier. You can see the glacier spanning to the sea. It's really beautiful. Dubai, obviously. I think all satellite operators are taking pictures of Dubai. But today, actually, yesterday, I took a picture of Beirut at the time of the conference. So actually, I think everyone is on that picture, if you zoom. Of course, you can see people, but this was yesterday. And fortunately, today, the weather is kind of bad, but yesterday was pretty good, so it looks like this. I just got it this morning and added it to the thing. Our next mission is called Wezunusat 1R. It's going to be kind of the similar tech, a bit lighter. In this case, we're going to remote sense all the polar areas. It's very interesting because actually, due to the ice melt, the polar cap melting in the north, it is opening new maritime routes to trade between Asia and Europe. So instead of going south, after Africa or even using Suez Canal, you can go up. The thing is, there are lots of icebergs, so you have to be careful. So using this thing, we're going to kind of track where the icebergs are, and we're going to help boats navigating in the area. And you don't need a very big satellite to do this. It's kind of a basic mission. So why not using this little thing here? We're going to launch it in a few months. It's ready, actually. So yeah, maybe for this one, you can start the video. So what I'm going to talk about is actually our new project, which might be interesting for a lot of users. We are developing a constellation. A constellation is a group of satellites that are orbiting together so that we can cover the whole globe every day. Is it working? So let me explain quickly before the video starts. Using our microsatellites, for the price of one big guy, we can launch 50 small ones. So we can make a constellation. And the point of launching a lot of small satellites is to have this global coverage, so that your Google map, for instance, will be actualized every day, which is not the case, actually. If you check the data of Google Map, it's pretty old, because they are buying data from big satellite companies that have maybe a few satellites that cannot take the whole Earth all the time. So this is our new video for, oh, it's a bit laggy, unfortunately. Anyway, of the new projects we are trying to develop. So after launch, we'll have a spacecraft like this, which is actually pretty small, and deploy. And what you will see is that you have two telescopes on the front. They're going to expand like this. And using this tech, we're going to, so remind that we'll have 50 of them. We're going to scan the whole planet using what's called a space train. So you're going to see on the video that actually the spacecraft are kind of following each other on the same orbit. And this is allowing us, because the Earth is rotating, to scan it. It's pretty nice, actually. So we don't have much to do, actually. We just let the spacecraft on their own orbit evolve. And yeah, you will see on the next thing. And it's going to kind of naturally scan the surface every day. This way. You see? The Earth's rotating, and we're just spanning over and taking pictures. Okay, so apparently this computer doesn't like the videos, but the idea is that if you can have pictures every day, you can start understanding on a time base what's happening. For instance, agriculture. We can predict if the harvest is ready or not. Or we can, for instance, if you're interested in shipping, for instance, by checking what are the assets on a harbor, for instance, you can see where are the boats, what are they doing, and you can kind of compute a lot of things. And these are just a few examples of the countless possibilities that you can do with this kind of system. So the idea is that we are not going to do everything. We are satellite makers. We are focusing on bringing the system and providing the data. But then the analysis is up to you, actually. How are you going to use this data to understand what is interesting for you? Thank you. So if you can come back to the slides. Yes. So briefly, the key points, 50 satellites, 80 kilograms each, 2.5 meters of ground resolution. This is important. The point is not tracking everybody. The point is actually taking lots of data, which is anonymized. So the point is, you barely see cars. You just see like aggregated data, fields, boats, you know. You don't try to understand who's doing what. You're trying to understand the big values. That's very important. And so one picture was going to be, it's called SWAF. It's going to be 57 kilometers wide. It's pretty big for this kind of machine. And we're going to start in 2017. So the idea is, you have the spatial axis, the whole globe, but also you have the time axis, which is what's missing nowadays. We already have a global mapping of the Earth. You just check Google Map, but the time is not coherent. You have different timings. Here, the idea is you can kind of go back in time and understand at one location what's happening. For instance, let me give you a few examples. Precision agriculture. So you can understand, as I said before, optimal fertilizing, harvesting, yield estimate, just by checking the colors. Or deforestation, forestry. You can check if you have assets, you can manage them. You can detect deforestation, for instance, because you can compare pictures from previous days and you can see the evolution of the field. Area marketing. So in this case, if you're a marketer, you might be interested in knowing what's the best location for your service or your shop. So by having the freshest data, you can analyze precisely and predict your impact on the market. Transportation logistics, you can count cars. So you can, for instance, assess parking lots. Are they full? Are they not? So you can kind of monitor, if your assets are well optimized for the task they're supposed to do. Traffic jam. You can also, if you're in urban development, you can start understanding what's happening if you have areas that you should optimize or not. Economic trends, by checking, containers or ships, you can kind of assess whole storage on the whole world, import, export, many things. Those are just a few examples. This one is really cool. Progress management. Oh, that was supposed to be a video as well. OK. Unfortunately, it doesn't work. But what you see here is a bridge. And on the video, you can see the bridge closing, because we take many pictures of the same area. What's important is, so you have this time lapse of what's happening on Earth. And so this is very interesting, because you can understand what is under construction, what is not, what is the progress, what is the time frame. And last but not least, disaster prevention and mitigation. When you have tsunami or forest fire or anything, this is actually a picture we took of a volcano in eruption. You can see the plume here over there. And if you can monitor them real time, then you can take the right decision to save many lives. Or if you think about Nepal, the assessment of the situation took a bit tough time, because to have the satellites on site, from the big companies, it took a bit of time, and to have the help coming and to assess the situation. If you have everyday monitoring, you can have shorter response time, and so you can improve. So the idea of this system is that in 2017, we're going to launch 3 first-generation satellites, the same type as I showed before. And then in 2022, we are planning to complete the constellation of 50 satellites. But this is the idea. This project is actually way too big for us, because we are a small company. And also, we are not trying to control everything. We want to have people coming with us, companies or associations, coming with us and participate. So we have many ways of partnerships, and we are thinking of. And one, for instance, which might be interesting is let's build satellite together. For some countries which might not have satellite technology yet, it's a good opportunity, because we bring our technology, we build it together, and then once the satellite is launched, it's part of the constellation, but because you've built it with us, you have privileged access to the data. Or another way is just, we'll generate petabytes of data. It's enormous. We'll need lots of, analysis power, and we are actually not even thinking of what all the potential applications, data analysis applications we can use. So we also need people that know how to analyze data, or companies that are interested in using our data to generate, meaningful insights. So, and the last thing, of course, support our growth. Investors are well welcome. Thank you very much.